Question 11 from Paper 2 of the 2024 Higher Physics Examination from the SQA. Spectral emission lines are unique to each element. These lines are produced when electrons make transitions between two energy levels, and photons of light are emitted as a result. The diagram represents some of the energy levels for a hydrogen atom. Now, part A says for the energy levels shown, determine the number of possible emission lines caused by the transition of electrons between the energy levels. Well, in this case, we be very systematic. An emission line is caused by the electron falling from a higher energy level to a lower energy level. So we start at the highest energy level and we make our systematic choices. So the first one could be straight down to this one here, or it could be straight down to this one, or it could be straight down to that one. Or there could be electrons sitting on this one, which goes straight down to energy level E0, or it could go down to energy level E1. And finally, there could be an electron sitting at energy level E1, and that would make just a transition down to there. So as you can see from the diagram, there are 6 possibilities of emission transitions there. So on the spectral lines, on the emission line spectrum, you'll get 6 lines from that particular energy level configuration. Now, part 2 says, identify the electron transition that results in the emission of a photon with the shortest wavelength. Well, we know that the energy of the photon, E, and that's the energy of the transition, energy difference between the energy levels of the transition, is equal to HF. Now, we can also write that down as its sister equation. We could change the F to HC upon lambda. So if we're looking for a wavelength with the shortest wavelength, that means this number is very small, which means the energy will be very big. So a short wavelength photon will result in the energy level transition, which is the biggest. And that looks like it's going to be from E3 down to E0. So we're looking for E3 down to E0 for answer A, part 2. Question 11 continued. Part B. An electron makes the transition from E3 to E1, and for 4 marks we have to determine the wavelength of the photon of light emitted. Let's take a look at the energy level diagram again, and we're going to go from E3 to E1, so I'll just mark that in. There we are, E3 electron sitting at, and it goes down to E1. It's going to emit a photon of light, and the energy of the photon of light which is emitted by that transition is exactly equal to the difference in the energy between the two energy levels we're looking at. Now, to do that, we just take the big number and take away the small number. That finds us the energy difference. So we have minus 5.45 times 10 to the 19 joules, but we can forget the minus signs because the minus signs just tell you how much energy is needed at that particular energy level to escape the atom. So the minus sign is just a convention. We can just ignore that, and we can say that delta E is going to equal to the energy level 5.45, the big number, times 10 to the minus 19 joules. Take away the smallest of the energy level numbers, 1.36. I'm just going by pure numbers, times 10 to the minus 19 joules. If we do that in a calculator, we get an answer of 4.09 times 10 to the minus 19 joules. Now, that will be the exact energy of that photon emitted. So we know that the energy of photon emitted, E, is always going to be equal to H times the frequency of the photon. But we're asked to find the wavelength of this photon of light, so we have to use the sister equation, and the sister equation is energy equals Hc upon lambda. All I've done is change the frequency into wavelength, wave speed c divided by the wavelength. So now I've got this equation here, I can rearrange, and I can find that the wavelength is equal to Hc divided by the energy of the photon, which worked out from the previous question, previous part there. H is Planck's constant, so we put in the numbers, 6.63 times 10 to minus 34 multiplied by the speed of light, 3 times 10 to the power 8, and we're dividing that by the energy difference between the transition, and that's going to be 4.09 times 10 to the minus 19 joules. So we put that answer into our calculator, we end up with an answer for the wavelength is going to equal to 4.86 times 10 to the minus 7 of a metre. Now we can put that into nanometers because that'll be helpful for the next question. So lambda is equal, just by moving the point, we get 486 times 10 to the minus 9 of a metre, and that's equal to 486 nanometers. Okay, so the wavelength of light of the photon given off in this emission, this transition from E3 to E1, is 486 nanometers. Now, in the last part of this question, we're asked to find the following. We're asked to find, well, for 1 mark, we're asked to state the colour of this photon of light. Now, if you're not sure, you go to your relationship sheet data book, and the data book is here. I'll bring a copy of it over like that. And the part we're looking for is 486 nanometers. So 486 nanometers, it's as shown there, 486 nanometers, so it's going to be bluish green, we can say for that. So the colour of the photon is going to be bluish green. 486 nanometers. Question 11c. The image below shows part of the line emission spectrum for a hydrogen atom. The red emission line is brighter than the others. For 2 marks, we're asked to explain why the red emission line is brighter than the others. Well, if that's the case, it's brighter, it means one thing, it means more electrons are making that particular transition that give off that red photon. And if there's more electrons making that transition, there's going to be more photons given off of that particular colour of light, and therefore the emission line will be brighter.